Welcome to the 48th online Spintronics seminar. Thank you very much for joining us. This is Xin Fan from University of Denver. It is my great pleasure to introduce our speaker today. Because of my mistake, we actually scheduled Professor Kyung-Jin to give a talk at also 12 a.m. midnight in Korea. I forgot about the daylight saving time change this month. Professor Kyung-Jin Lee is a KAIST chair professor at the physics department of KAIST. He received his bachelor's, master's, and PhD degrees from KAIST and was a postdoc from 2003 and 2005 at Spintech. He has worked at Korea University for 15 years and recently moved to KAIST. His research area includes theoretical and numerical study on magnetization dynamics and spin transport. His research focuses on improved understanding of current-induced magnetization dynamics and the development of a new class of spintronic devices based on spin torques. He has authored about 200 papers and about 30 issued patents, and has been a frequently invited speaker at magnetism and spintronics related conferences. Professor Lee is a recipient of many awards, including Excellent Patent Award from Korea Patent Office, awards for excellent research achievements from Korea Magnetic Society, and KIST. He's also an advisory committee member of IEEE representative in the 3M from 2013, and is a program co-chair for Intermag 2021, a publication co-chair for Intermag 2023. So without further ado, Professor Lee, can you take it from here?
Thanks for the introduction. And first of all, I would like to thank Krill and Sin for this very nice Spintronics seminar. So today I'd like to talk about the magnetization, dynamics, and spin transport in compensated ferrimagnet. So my talk will consist of two main parts. The first half is for the magnetization dynamics, and second half is for the spin transport. And each has several subjects. So let me start with a brief introduction about Spintronics, even though you know all about this. And Spintronics include many sub-branches, including the electrical spin generation, mechanical motion, geometrical spin variphases, and so on and so on. And we are also very interested in applications. For example, magnetic random access memory, MRAM. The embedded version was commercialized last year. Now people are trying to find out new applications based on the MRAM. One example is this integer factorization using the stochastic magnetic tunnel junctions, or called PBIT. Also, there are ongoing efforts for realizing the race train memories based on the manual and Skyrmion motion. And also the spin torque nano-oscillators may find use for the neuromorphic computing. All these fundamental and application research area are mostly based on the ferromagnet, because ferromagnet is a good spin current generator, and also it is very good spin current detector. And we know that using the spin transfer or spin orbit torque, we can switch the magnetization, which is useful for non-volatile memory and logic applications. And also they can move the domain well and Skyrmion. So because of this long history of the research approach, the physics about the spin transport and magnetic dynamics in the ferromagnet is more or less understood. But when you consider the application, for example, the switching current for MRAM application is not sufficiently low if you want to expand the market of the MRAM. If you consider domainal speed for SRAM displacement, the ferromagnetic domainal can move very fast, but still it's not sufficiently high. So when you consider the Skyrmion devices, there is an interesting but detrimental effect called the Skyrmion Hall effect that causes the information loss. And now there are ongoing research approach for antiferromagnet. With hope that they are qualitatively different from the ferromagnet in many aspects, and it may help to resolve these issues. Actually, there are many review articles about the antiferromagnetic spintronics, including this review cluster published in Nature Physics and also in the Review of Modern Physics in 2018. So in my talk, I will talk about the compensated ferrimagnet instead of the true ferromagnet, and I will explain why very soon. So the first half is for the magnetization dynamics in ferrimagnet. This part includes the fast ferrimagnetic domainal motion and vanishing Skyrmion Hall effect, and also the enhanced magnon-photon coupling in ferrimagnet. So we focused on the layers transition metal ferrimagnet, and one simple reason is that this material have two different compensation temperatures or compensation conditions. One is called TM. This is magnetic moment compensation point. The other one is TA, angular momentum compensation point. The region is as follows. For example, in the cobalt gadolinium ferrimagnetic alloy, these two magnetic moments are antiferromagnetically coupled. And interesting thing here is that the Landau factors are different. And as you know, the spin angular momentum is related to the magnetic moment M through the gyromagnetic ratio gamma. This gamma includes material dependent parameter Landau factor. They are different, which means that if you consider the variation of M as a function of the temperature, so this is layers element M, this is transition metal element M, because this is kind of antiferromagnet, so they have opposite sign. So when you add up these two, you can have this middle red line. And you see that at some temperature called Tm, the net magnetic moment is 0. This one is called magnetic moment compensation temperature. But because of these different Landau factors in cobalt and gadolinium, when you consider the net angular momentum, this one, net angular momentum becomes 0 at a temperature Ta, which is different from Tm. So the difference comes from the difference in the Landau factor. And as I will explain, the magnetization dynamics is governed by the angular momentum or spin density, not by magnetic moment, which means that Ta shows at Ta, the magnetization dynamics is antiferromagnetic, but at Ta, we have a finite net magnetic moment, which means that we can control the magnetic textures by using the external magnetic field. So the first one is field-driven ferrimagnetic domainal motion in the vicinity of Ta. This work has been done in collaboration among Tero Ono's group, Kyoto University, Yaroslav Kovnyak's Kwangim, UCLA, Chukamoto, Nihon University, and my group. So let me first introduce the antiferromagnetic domainal motion theory by spin orbital. The resultant equation is this one. So this is antiferromagnetic domainal motion velocity is proportional to B sub D. Here B sub D is the magnitude of damping lags torque, and of course that is proportional, linearly proportional to the current density. So concerning the ferromagnetic domainal motion, the equation is shown here in the presence of the DMID. It is a little bit complicated, and when I plot simply these two equations using the same parameters, I have this result. So the ferromagnetic domainal motion, domainal velocity first increases with current, but then saturates because of the balance between the DMI and SOT. But in case of antiferromagnetic domainal, as you can easily see from this simple equation, the domainal velocity is simply linear with current. It means that at some point of the current, the antiferromagnetic domainal speed is much higher than that of the ferromagnetic domainal. The reason is that there is no domainal tilting in the antiferromagnetic domainal motion, as I will explain shortly. Okay, so spin dynamics is given by this Heisenberg equation, spin operator and relevant Hamiltonian. Then we get the equation of motion. Then we convert it into the M because we are more familiar to M. So then you have this equation, looks very familiar. This is the precession torque term in the Landau-Lipsch-Gilbert equation. So bottom line here is that actually we derived equation based on the angular momentum, which means that the time evolution of the state or dynamics is given by the commutation relation between the spin angular momentum and relevant Hamiltonian, not between the magnetic moment and relevant Hamiltonian. So spin is more important for, spin density is more important for the dynamics. So the conversion to M is just because we are more familiar with M, or experimentally easier to detect. In the single element ferromagnet, or in that case, it does not make any change because as is M, simply multiplied. But in ferrimagnet, it's different because at TA, this S total is 0, but M total is non-zero. So the spin dynamics of the ferrimagnet is antiferromagnetic at TA, but magnetic field works. And as a result, field-driven antiferromagnetic spin dynamics is possible. So we derived equations of motion with two collective coordinates for the ferrimagnetic domainal using the domainal position x and domainal angle phi, and we got these two equations of motion. The first one is called force equation, and the second one is called the torque equation. So if we are familiar with this kind of Phys equation, you can recognize that there is a second order time derivative. This does not appear for the ferromagnetic domainal, but because this one, ferrimagnet has antiferromagnetic texture, so we have this one too. So in these equations, the important term is this G, called gyrotropy coefficient, that is proportional to the net spin density. So at TA, this net spin density, or delta S, is 0, then this G is 0. So I can drop these two terms here. Then you can find that the first equation is now the function of only x, and second equation is now the function of only phi, which means that x and phi, so domainal position and domainal angle, are completely decoupled. And here F is the force. So if you apply the field, this is the field. If you apply the torque, the spin-orbit torque, spin transfer torque, this is the torque term. So this force actually moved the changes the x, it doesn't change the phi. In other words, all the forces is now using to move to cause the translational motion of the domainal. It is not used for the rotational motion of the domainal angle. That is very important point. So based on this collective coordinate approach, we could obtain the equation for the ferrimagnetic domainal speed driven by the magnetic field H. Here alpha is damping, M1 minus M2 is net magnetic moment, and S is the sum of two sublattice angular momentum, and KD is domainal anisotropy and so on. So second equation is for the work breakdown field. So at Tm, this M1 minus M2 is 0, and therefore domainal velocity is 0. And that is quite reasonable because there is no Zeeman coupling, so there is no field-driven domainal motion. But at Ta, delta S is 0. So when you look at this equation, this term becomes 0. Then domainal velocity may be maximized at Ta. And when you look at this Walker breakdown field, delta S appears here, which means that at Ta, the Walker breakdown field goes to the infinity. In other words, there is no Walker breakdown phenomena at Ta. So the Terry-Onus group carried out the experiment using this iron, cobalt, gadolinium antiferromagnet. They have compensated ferrimagnet. They first measured magnetization compensation temperature by measuring the anomalous Hall voltage or resistance as a function of the outer plane magnetic field. At low temperature, it is clockwise, and at high temperature, it is counterclockwise. And at around 210 K, the coercivity becomes very large, and this temperature is corresponding to Tm because at Tm, net magnetic moment is 0. So you need infinite field to switch the magnetization. So when they plot coercivity, it becomes maximum at Tm, or when they plot the sign of this anomalous hole resistance, it changes the sign at the tank temperature. So in this sample, the Tm is found to be around 220K. And they measured domain velocity as a function of the field at various temperatures, and the result is summarized on the right-hand side. So this one is Tm, 220K, but what we observed is that domain velocity becomes maximum at very different temperature, 310K. And so according to our theory, this temperature is corresponding to TA. So we performed the theoretical and numerical studies. Here, lines comes from this equation that I have showed before, and the symbols are obtained from the numerical modeling based on the atomistic energy equation. And you see that they show good agreement, and more importantly, domain velocity becomes maximum at when the delta S is 0. So this is corresponding to TA. So which means that this temperature is TA. So this result shows two things. One is that the domain velocity can be very fast at TA because it is antiferromagnetic. It's like antiferromagnet. And another thing is that usually it is easy to measure Tm because you can simply measure the hole resistance, but it is usually uneasy to measure the TA. But when you do the field-driven domain motion measurement, you can experimentally determine the TA of a specific sample because the domain velocity becomes maximum there. Okay, the second one is the vanishing Skyrmion Hall effect of the RETM ferrimagnet at TA. And this work has been done in collaboration with the Terrell Honors Group, Kyoto University, Yaroslav Sokovnyak and Sekwon-Kim, UCLA, Professor Tsukamoto's group, Nihon University, and so Seokbong Chess Group, Seoul National University, and our group. So there are a lot of interest in the magnetic skyrmions because that can be very small as 10 nanometer and fast and move at low current. And more importantly, it is defective insensitive. For example, in this modeling result, this head-sheet region is the mechanical notch. And usually when you push your domainal through here, then domainal usually pinned here because of the strong pinning potential. But in case of skyrmion, it can avoid this pinning potential and straight show the still motion. It's because of their topological nature. But later people found that there is an interesting but detrimental phenomena called the Skyrmion Hall effect. For example, in this experiment, mock image, they injected current in the horizontal direction, but the skyrmion, this black dot here or white dot there, they move not only along the horizontal direction, but also in the vertical direction. So it's like a Hall effect. So it is called the Skyrmion Hall effect. From the charge Hall effect, we know that it originates from the Lorentz force because of elementary charge Q and L dot is the velocity and this external magnetic field. Actually, the physics behind the Skyrmion Hall effect is quite similar to the charge Hall effect because we have a topological charge, which is given in this form, where n is order parameter. In the antiferromagnet or ferrimagnet, this is Snell order parameter. So it comes from the texture. So the skyrmion has either +1 or -1 of this Q. And also, even though we do not have a true external magnetic field, but there is a fictitious magnetic field that is proportional to the net spin density. Because this B field is proportional to the net spin density, two theory papers predicted that the Skyrmion Hall effect must vanish in antiferromagnet, because in antiferromagnet, the delta S is 0. However, to my knowledge, there is no experimental result yet. I think it is because It's easy to control the antiferromagnetic texture or generate antiferromagnetic skyrmions. So we wanted to do this measurement about the Skyrmion Hall effect based on using the ferrimagnet gathering iron cobalt. Here we have a platinum layer to inject the spin orbital. The first we measured the DMI field of this sample. It's about 60 millitesla, which is much larger than the domainal hard axis anisotropy, which is about 1 millitesla, meaning that this sample has a very well-defined topological charge Q. Then we measure the field-driven domainal velocity and found that it is maximum at around 280 K, which is identified as angular momentum compensation temperature TA. Then the Terrio Ono's group fabricated this complicated device structure, and it includes this current line. Here you see the happening structure. The reason of this happening structure is that when they inject the current, then voltage field concentrate at this region in the direction pointing into this slide or the opposite direction, and it may nucleate the skyrmion or a bubble. So this is the mock image. So you see that there is a bright region, bright circle here that is nucleated bubble. And the other region is relatively darker, so it means that the magnetization interaction is opposite between this and the darker region and bright region. And then they inject in-plane current through the platinum. Unfortunately, we couldn't observe the motion of this bubble. Instead, we observed elongation of this bubble. It is because during the lithography process, there would be a strong pinning potential, and then the bubble cannot escape from this pinning potential. So anyhow, we found there is an angle of this elongation, and we wanted to understand what this angle means. So we repeat the same measurement by reversing all the magnetization directions. So now bubble is darker and the rest of the part is brighter, meaning that here magnetization is down, here magnetization up, and so on. Then we repeat the same measurement by injecting the current. The bubble still elongates, but the angle changes its sign, but with the same magnitude, similar magnitude, which means that this angle reflect the topological charge, because Q, let me go back to the equation here, this Q include n 3 times, so the odd function of the Nel order parameter, meaning that if we reverse the sign of n, then Q reverse its sign. So we thought that what we observed is half skyrmion motion. So one edge is pinned by uncontrolled strong pinning potential, but the other edge moves, and that causes this elongation of this bubble. And at the other edge, because of the strong DMI field of the sample, the kind of texture or skyrmion-like, half skyrmion-like texture is well preserved. So we carried out the same experiment at various temperatures. So at 340 theta is negative, 280 almost 0, and 253 it is positive. And the results are summarized here. For magnetization up bubble and magnetization down bubble, they are kind of mirror symmetry and quite linear with temperature. And at 280 K, it becomes 0. And as I told before, this temperature is the angular momentum compensation temperature of this sample. So it means that the Skyrmion Hall angle is related to the net spin density, and at TA, this net spin density is 0, and therefore Skyrmion Hall angle is 0. So we also carried out the modeling study and obtained qualitatively the same result. When we change the net spin density, it becomes 0 for Q is plus 1/2, and or Q is minus 1/2. So it is reproduced. Okay, the third one is the enhanced magnon-photon coupling at TA. This work has been done in collaboration with Jae-Chul Kim, Se-Kwon Kim, and Seok-Jong Kim. So as you may know, there is a field called cavity spintronics. What they want to do is to make a coupling between the microwaves or photons and magnons. They usually use the E example in a cavity. One of the reasons of this research field is that in quantum information processing, photons in a cavity mediate qubit from one physical constituent to another. So people want to use the spin ensemble for storage and transduction of this qubit information. So one of the examples is shown here. So this horizontal line is corresponding to the microwave frequency that is fixed by this cavity. And this line is corresponding to the magnon frequency. So that varies with the external magnetic field. When they meet, the anti-crossing occurs, and the size of this anti-crossing in unit of the frequency is called the magnon-photon coupling strength, omega. And this omega is proportional to the square root of the number of spins. Then people try to use the ferromagnet because ferromagnet has high density of the spin, high spin density. So then we thought that what happens for ferrimagnet? So we derived we solved the coupled equation, so magnon oscillator and the cavity oscillator for the ferrimagnet. We found that the coupling efficiency can be approximated in this form. So here, two parameters are important. One is m sub L, that is net moment, and the other one is delta S, net spin density. So at TA, this net spin density becomes 0, and therefore this part becomes maximized. But still, we have finite m sub L, and therefore this omega over small omega may be maximized. And we plot this equation as a function of delta S at various anisotropic Ku, and we found that it is the case. This coupling efficiency becomes maximized at TA, and this, according to the used parameters, this point is corresponding to the magnetic moment compensation point, but you see that there is nothing, no special variation. So TM is irrelevant to the magnon-photon coupling, but TA is very important for the magnon-photon coupling in the ferrimagnet. Then we compared three classes of the magnets: ferrimagnet FIM, antiferromagnet AFM, and ferromagnet FM. So figure A shows the excitation frequency or resonance frequency as a function of the field. The ferromagnet is the lowest, and antiferromagnet and ferrimagnet, they are similar, but ferrimagnet is more sensitive to the field because it has net moment. And figure B shows the magnon-photon coupling strength. The antiferromagnet is the lowest and ferrimagnet is the highest, which means that the strong magnon-photon coupling at a high excitation frequency can be realized at TA of the ferrimagnet. So let me summarize the first half for the magnetization dynamics in ferrimagnet. So we found that the field with nominal motion can be fastest at TA because the Zeeman energy is used only for translational motion, not for the rotational motion. And by the same reason, so the suppressed spin rotational motion gives rise to the vanishing Skyrmion Hall effect at TA. And because of the antiferromagnetic dynamics combined with finite Zeeman coupling, enhances the magnon-photon coupling at TA. Okay, so let me move on to the second part, that is the spin transport. Two small items. One is coherent length of transverse spin current, and the other one is enhanced non-adiabaticity of spin current for domain of motion. For the first one, this one has been done in collaboration with Hyun-Soo Yang's group, National University of Singapore, Professor Aono's group, Toyota Tech Institute, Professor Chu, Tongju University, and my group. So this is the same argument. The dynamics of any operator can be calculated by that operator and the commutation relation between that operator and relevant Hamiltonian. In our case, X is S, spin operator. And for the spin transport, this Hamiltonian is the SD exchange. Then we get this dynamic equation of motion in time. So when you change it into the space, then still we have this precession pattern. For example, when you inject a single electron with this polarization in this direction to the magnet, ferromagnet, then it precesses around this background magnetizing direction because KF, the Fermi wave vector for upspin and downspin are different. This is for the single electron, but in reality, we have many, many electrons with different wave vectors. So when you apply the electric field, then there is a small shift of the Fermi surface. Then this region gives the positive contribution. This one is negative contribution for the current. So let me assume that I have this spin barrel structure. Fixed layer is magnetization is pointing in this direction and free layer is pointing in that direction. So if I inject electron from here to there, that is polarized along the y direction and enters into the magnetic ferromagnet with magnetization in the z direction. So when I plot Sy for this K state, this Sy component will oscillate because of the precession. But we have not only this one, but also this K state electron. And this one has smaller X component when you project K vector along the X direction. So K is smaller and therefore wavelength becomes longer. We have also this green one with longer wavelengths and even blue one with even longer wavelengths. So what we have to do is we calculate this kind of precession pattern for all case stage on the Fermi surface and sum up. Then the result is this one. So your transverse spin current will be absorbed by the ferromagnet within the thickness, very short, about half period of the precession. This thickness is called the ferromagnetic coherence length or the spin coherence length of the transverse spin current. And according to the free electron model, that is inversely proportional to the difference of Kf up and Kf down, or approximately this inversely proportional to the SD exchange strength. So when you use the free electron model, this number is about 1 nanometer, I think, but in reality, the Fermi surface shape is much more complicated than assumed in the free electron model, which means that there is more out of phase than expected in the free electron model. So the lambda c spin coherence length is actually much shorter than the 1 nanometer, which means your transverse spin current is abruptly absorbed at very interface of the ferromagnet. So spin torque for ferromagnet is surface torque, and spin torque efficiency is inversely proportional to the ferromagnet thickness because everything is determined at the interface, but when you increase your thickness of ferromagnet twice, you need twice larger current to get the same effect. But the situation becomes very different in the antiferromagnet. According to this theory paper, they calculated the spin torque in antiferromagnetic spin bulb. This is antiferromagnet, this is antiferromagnet, separated by paramagnets or non-magnet. This is the main result. The Slonjevsky spin torque is a function of the location. So you see that the spin torque alternating on the atomic scale, but the magnitude doesn't change, which means that the spin density is uniform because the spin torque is given by exchange interaction and magnetic order parameter cross product non-equilibrium spin density. In antiferromagnet, this magnetic order parameter is alternating. So this complete alternating on the atomic scale means that non-equilibrium spin density was transverse component of the spin is uniform in this calculation. Because they assume very ideal antiferromagnet without any defect and so on. But bottom line here is that the transverse spin current can go much further in the antiferromagnet. What happens for the ferrimagnet, RETM ferrimagnet? So let me go into a little bit detail of this band structure. So transition metal, cobalt ion nickel, we know that the 3D is 3D electrons, 3D spins is mainly responsible for the magnetic moment, and 4s is responsible for the spin transport, but still there is strong SPD hybridizations. In case of layers element, 4f band is mostly responsible for the magnetic moment, and 5d, 6s are responsible for the spin transport, and there is exchange coupling between 4f and 5d6s electrons. So this is the Fermi level. TM, transition metal element, 3D band is located around Fermi level, and they are half-filled, above half-filled. And in case of layers element, 4f is here, so usually located about a few electron volts below the Fermi energy level. But the 5D is at the Fermi energy. So first, there is an intra-atomic ordinary exchange. So 4f spins in early element create positive local 5D moments through the ordinary 4f 5D exchange. And because of this above half filling and below half filling, this RE 5D element and TM 3D element, they are antiferromagnetically coupled. Okay, so when you inject the current, it is mostly flow through this Fermi level. It sees both, for example, down 3D spins, but also up the 5D spins. And it experience some kind of antiferromagnetic order, but it is not perfect antiferromagnetic order because of the different density of state or different spin polarization P. According to this experiment, low temperature experiment using, I think, undirect reflection, the cobalt, the polarization of cobalt is about 40%, but the polarization of gadolinium, spin polarization of gadolinium is about 10%, which means that your conduction electron spin will experience the antiferromagnetic order, but it is not perfect, only partial antiferromagnetic order. So when we think of the spin transport through partly antiferromagnetic order in ferrimagnet, if it is the ferromagnet, this is a magnetic moment. The deflect vectors are spin direction, the classical, semi-classical picture. It rotates at every magnetic moment, and it gives the very strong out of phase, as I explained before. But in case of ferrimagnet, at site A, it rotates clockwise, but at the next site, site B, magnetic moment is in the opposite direction, so antiferromagnetic order. So coming back, the rotate clockwise and slightly anti-clockwise, and so on and so on. So the precession length becomes much longer than that of the ferromagnet. So we expect that the spin current length would be much longer in ferrimagnet than in ferromagnet. So we calculated that using a simple tight binding model, and this is the result. This is the spin torque. This red one is for the ferromagnet, and it shows very good agreement with well-known one-over-thickness dependence. But in case of ferrimagnet with different antiferromagnetic ordering, it shows much longer kind of wavelengths, meaning that the coherence length of the ferrimagnet would be longer than that of the ferromagnet. So the Hyun-Soo Yang's group carried out the experiment. They compared two samples. One is cobalt-nickel ferromagnetic multilayer, and the other one is cobalt-terbium ferrimagnetic multilayer. And both have the platinum bottom or top. And they carried out well-known the harmony Hall measurement to measure the spin orbital. And you see that this is the Dempelek torque signal. The blue one is Dempelek signal. So they have opposite sign, but it's reasonable because in the cobalt nickel, platinum is at the bottom, but here platinum is at the top. So the sign should be opposite. So they estimated the effective spin-orbit field as a function of the thickness of the cobalt nickel here, left column, and cobalt terbium in the right column. So the spin-orbit field in the ferromagnetic cobalt nickel, it decreases with increasing the temperature as expected. And spinel angle is more or less constant. And the switching efficiency that is defined by the defining field divided by the switching current density also decreases with increasing the thickness. This is well and consistent with what we have understood about the ferromagnet. But in case of ferrimagnetic cobalt terbium, the result is surprisingly different. The spin orbital increases and then decreases, and the spinel angle is not constant at all. And the switching efficiency also increases and then decreases. The number-wise, here effective spinel angle for the ferromagnetic cobalt nickel is about 0.25, but here it reaches number 2. So it's very different. But we could not conclude this is on evidence of the spin coherence length because ferrimagnet has well-known property that when you change the thickness, the magnetic property changes. For example, this MS changes as a function of the thickness of the ferrimagnet, and for example, around T7 nanometer, it is the magnetic moment compensation point. And around 7 nanometer, not exactly, but we have some kind of peak here and somewhat shifted, but still peak. So this strange result, we do not know if it is caused by this thickness-dependent magnetic property or it comes from the long spin coherence length. So we decide to do more direct measurement, that is spin pumping measurement. So we put cobalt copper bilayer on top of multilayers. In case of cobalt nickel ferromagnetic multilayer, that has perpendicular magnetization, and this cobalt top layer has in-plane magnetization. We put it into the AC field environment, and it starts to precess, and it emits the spin current through the spin pumping process. This spin current carries the spin polarization of this in-plane cobalt. Therefore, that is transfer spin current to this perpendicular magnetization of cobalt nickel. In case of ferromagnet, it should almost completely absorbed at the interface here, and therefore no current can reach at the platinum layer. So we expect there is no inverse spinel effect. But in case of cobalt terbium, and if this one has longer spin coherence length, this spin current can reach at least partially until the platinum layer, then we could get the inverse spin Hall effect signal. Okay, so this view graph shows the inverse spin Hall effect signal as a function of the bias field. So this is the control sample, the reference sample. Platinum copper cobalt shows the largest peak. And when we insert cobalt nickel about 1 nanometer between platinum and copper, all signal is gone, which means that transfer spin current originating from this top cobalt layer is almost absorbed at this interface. It cannot reach to the platinum layer. But when you insert cobalt terbium 5 nanometer, we have a peak here, even reduced, which means that some portion of the transverse current still penetrate this cobalt nickel multilayer and reaches the platinum layer. As another reference sample, we remove the top cobalt layer, so we remove the spin pumping source, but with the cobalt turbine multilayer, still there is almost no signal. So this red data comes from the spin current originating from the spin pumping of the in-plane cobalt layer. And also, if we use only cobalt turbine bilayer, there is no signal, which means that here cobalt turbine itself does not contribute to the inverse spinel voltage. So we conclude that this is an evidence of relatively long spin coherence length of the ferrimagnet. The next one is spin transport torque-driven antiferromagnetic nominal motion in the vicinity of angular momentum compensation point TA. This work has been done in collaboration with the Kyoto University, UCLA, Nihon University, KAIST, and my group. And this one is very similar to the first topic, field-driven nominal motion, because we used almost exactly the same setup, except for we inject now current in the presence of the magnetic field. So we inject the plus current and minus current and compare the result and try to find out what is the spin torque contribution. In this sample, we do not have heavy metal and they are nominally symmetric, so we expect that there is no spin orbital contribution. So when we add up these two velocities obtained from the positive current and negative current, but at the same magnetic field, it should be identical to that of the field-driven dynamics. But when we subtract these two velocities, then we have two spin torque contributions. One is adiabatic torque, the other one is non-adiabatic torque contributions. Here, beta is the so-called non-adiabaticity, and alpha is damping, P is the spin polarization. Okay, so let me first assume what is expected spin torque induced domain velocity as a function of the temperature, or theoretically delta S. Here we assume that the signs of spin polarization and beta do not change at TA. So concerning the spin polarization, it is for sure because, as I showed before, gadolinium spin polarization is 0.1 and cobalt spin polarization is 0.4. So at TA, TA is mostly given by the layers contribution that does not contribute to the spin polarization of the gadolinium. So P should not change the sign at TA. But beta, we don't know because beta is a very difficult number. Anyhow, the adiabatic spin torque looks like this function. So it looks like anti-symmetric Lorentzian. So when you change the delta S, then it changes its sign. So for positive P, it's black curve, and negative P is red curve. And the non-adiabatic contribution looks like symmetric Lorentzian. And so and its sign is determined by beta P, the sign of the product of beta P. If beta P positive, it is black curve, and beta P negative it's red curve. So we carried out the experiment at various temperatures with plus current and minus current in the presence of the magnetic field. At 211 K, the plus current shows slightly higher velocity. 260 K, blue one. So negative current shows a little bit higher velocity, and 240 K, they are very similar. So we first add up these two velocities obtained from plus J and plus current and minus current, and we determine the TA, which is 241 Kelvin of this sample. And then we subtract the result and obtain this experimental result, and it looks like the combination of the symmetric Lorentzian and anti-symmetric Lorentzian. So we decompose this experimental result into symmetric one and anti-symmetric one. And then we compare the sign of this experimental fitting result with the theoretical one. So antisymmetric component shows that this plot, meaning that P is positive. And symmetric component shows that this beta P corresponding to the negative beta P, because P is positive, then beta is negative in this sample. Because we have equations, we try to get the fitting parameters, and what we obtained is as follows. The damping is 0.003, and beta is -0.5, and P is about 0.1. So polarization 0.1 is reasonable, but first of all, the damping, we thought the damping is too small, so we carried out another independent measurement to determine the damping, and in this paper we found that damping is 0.007, but twice different, but still same order of magnitude, which means that the damping is very small in the ferromagnet. Very surprising fitting result is this beta term. In comparison to the alpha, it's very large and the sign is negative. We don't know why, but we thought that this large beta should be related to the antiferromagnetic ordering. And negative beta, there is a theory from this paper that actually when you consider the band structure, beta can be either positive or negative depending on the details. For example, if the system has both hole-like and electron-like carriers at the Fermi level, then beta can be negative. So we carried out linear response theory in a tight binding model calculation for the spin transport torque of the domain wall. So these two top panels is for the ferromagnet domain wall. Bottom two are for the antiferromagnet domain wall. Left column is for the adiabatic torque. Right column is for the non-adiabatic torque. There is Fermi level. So you see, and here, horizontal axis is the domain wall width. So in case of the ferromagnet domain wall, adiabatic torque is constant and non-adiabatic torque is constant. So we can determine the beta term by dividing these two. But in antiferromagnet, the result is quite different. The adiabatic torque contribution is almost zero, but non-adiabatic contribution is non-zero. And one important difference from the ferromagnet is that it is very sensitive to the domain wall width, and it rapidly increases as the domain wall width decreases. And actually, when we look at the special profile of the torque, you see that there is some oscillating component. This oscillating component arises from the spin precession. And it is actually a known effect in the ferromagnet that is called the spin distracting process in this originally in this paper and also later calculated in this paper too. So we thought that the enhanced non-adiabaticity originate from the spin distracting process, and that is actually in line with the longer spin coherence lengths. They share the similar physics. Okay, so let me summarize the second part. We found that the compensated ferrimagnet, even though it does not have a perfect antiferromagnetic order, it has a partly antiferromagnetic order, but it can be used to study the spin transport through the antiferromagnetic order. And what we found is that coherence length becomes longer, and also the non-adiabaticity for the domain wall, ferrimagnetic domain wall, is largely enhanced. We thought it we attributed to the enhanced spin distracting process due to the antiferromagnetic order. Thank you for your attention.
Thank you very much, KJ, for the very interesting talk. So it's time for questions. If you are in Zoom, please use the raise hand function. You can do that by clicking participants, and in the popped up the participants menu at the bottom, you should be able to find a raise hand button. If you have trouble finding that, you can always send me a private message. And if you're on Twitch, please just type your question in the chat box and I will read it for you. Matthias, do you want to go ahead with the first question?
Yeah, thanks, Kyung-Jin. Very nice talk. I have a question about the spin transport you said in ferromagnets was very short due to the fast dephasing. Now, this only holds for electronic spin currents. How about for magnetic spin currents, and in particular for the case of magnetic insulators?
You mean magnon spin current or
yes. So,
magnon spin current?
Yeah, if you have 1 nanometer spin dephasing length for electronic spin current, I completely agree. But for magnon spin current can be longer.
I don't disagree, but I have not thought about that for the magnon current.
Okay, thanks.
Actually, Matthias, just to chime on this thing, I think the dephasing only occurs for the transverse spin, so the spin polarization is perpendicular to the magnetization propagates in. I think a similar things will apply to insulators. If your spin is perpendicular to magnetization, everything will be absorbed at the interface, so you cannot generate a magnon spin current flowing through the insulator. Does that? Because the magnon spin current is when it's generated, its spin should be parallel to the magnetization or anti-parallel. Maybe or maybe not.
Do you ask to me?
No. Oh, so is it? Yeah, I was just want to also comment on that question. But well, is it because the dephasing is only about the spin perpendicular to the magnetization, right?
Right, and the main reason of the dephasing is that electron spin current, it comes from the difference between the Fermi wave vector for upspin and Fermi wave vector for downspin. So can we make the same argument for the magnon current, magnetic insulator? I'm not sure.
That I don't know, but I thought experimentally when people generating the magnon spin current, the spins are usually either parallel or anti-parallel with the magnetization.
Yeah, I think that it's very different situation. It's long distance the spin current, right? Not the transverse one. Then the story is very different.
I see. Is there another question?
In the first part of your talk, I just have a clarification question. Is S the, you say S is the angular momentum, is that spin plus orbital, sum of the spin and the orbital momentum?
Yeah.
So it includes the S, your S is L plus S.
Yeah, effectively describe this S includes both spin contribution and orbital contribution, and also this M includes spin contribution and orbital contribution.
Okay, thank you.
Satoru, please go ahead with the question.
Hi, Kyung-Jin. Yeah, thank you very much for the nice talk. You know, collection of very nice studies. I have a question about the low damping, low Gilbert damping that has been reported for compensated ferrimagnets.
Yeah.
So I understand, from what I understand, this seems to, you know, match up the all these experimental results from domain wall motion. But I guess my question is, has there been some kind of FMR experiments or FMR-based experiments that back up that corroborate, I guess, the low Gilbert damping and compensated ferrimagnets?
So if I remember correctly, we did it and we published it in a paper in Applied Physics Express, I think. And what we found is that so there is a line width, okay? And if you use the equation for the ferromagnet, then the damping seems to be very large, but it's incorrect because the equation is importantly different from, for ferrimagnet, the equation is different. And if we use the ferrimagnetic equation, then damping is still small. That is what I remember.
Okay, I'll look for this Applied Physics Express paper then. Yeah, thank you.
Yeah.
You have other questions? Okay, I just want to ask a quick question. So typically, the ferromagnet actually at the compensation temperature behaves very similar to the antiferromagnet. So it allows you to study the very interesting properties. But in terms of the application, that means we only have a very narrow temperature window to operate if you want to take advantage of that. Do you know if there's any potential way to actually broaden that temperature, make the TA or TM broader than it is currently at?
I had a similar question, so I asked it to my collaborator, Professor Tsukamoto, who provided the sample, and he told me that there is a way, but he didn't explain the detail. So I don't know about the experimental part, but there is one paper from Jeffrey Beach about the current-driven dominal motion in the Ferrimagnet. So in our field-driven dominal motion, the temperature range is very narrow, but in there, and also the Ruchel Rius, the Ferrimagnet dominal motion paper, the temperature range is quite broad. It's wider than the 100K. So, and still the dominal velocity is quite fast. So then it's okay, even though it varies with temperature, but if the value is over the target value of the specific device, then I think it's fine.
Thank you very much. Do you have other questions? Alexei, please go ahead with the question.
So I have a question. So if transverse spin current is not completely absorbed at the interface in some of those scenarios, so then the theory of spin orbit torque should be revisited, or like there could be some additional possibilities for spin orbit torques excited in ferrimagnets.
I believe so. Yeah. So actually, I don't understand this data. Theoretically, I don't know why. So they used quite a reasonable experiment and they used quite well established the interpretation, because this has been done by harmonic core measurement at extremely low frequency, kilohertz, meaning that the special feature of antiferromagnetic dynamics in the ferrimagnet doesn't appear here. So it's just a setting measurement. So I believe the ferromagnetic equation can work here. But then this result is quite, I cannot understand. I believe that there should be, I think, important missing part in the theory. I don't know what it is.
All right. Yep. Thank you.
Do you have other questions? Okay, looks like we're out of questions at this moment. So I want to thank you again for the very interesting talk.